Alrighty, one more section in this chapter. Hopefully you're not getting too overwhelmed with all of the math. There is a lot of math in this particular chapter. Stoichiometry tends to be that way. But this last section is on percent composition, and it's not nearly as complex nor as complicated as some of the combustion analysis problems you've been working the last couple of days. So hopefully this will allow you to breathe a little bit easier as we finish up this chapter on stoichiometry. This first sample problem that we're going to work today says, what is the percent composition for each element in calcium phosphate? And so calcium phosphate obviously is going to have calcium in it, and the phosphate ion, which hopefully you have memorized by now, is a PO4. Phosphate has a -3 charge. Calcium, being in the second column, has a +2 charge. So in order to balance the charges, I'm going to need 3 calciums and 2 phosphate ions. Now, if it wants to know the percent composition of each element, I'm going to have a percent for calcium, I need a percent for phosphorus, and I will need a percent for oxygen. Okay? Percent, in its simplest definition, is just the part over the whole. So the first thing that you're going to need to do is calculate the molar mass for calcium phosphate. And if you look at the periodic table in the front of the book, you will see that your calcium has a molar mass of 40.08. You will see that your phosphorus has a molar mass of 30.97. And you will see that oxygen has a molar mass of 16. There are 3 calciums, there are 2 phosphoruses, and there are 8 oxygens. And so when you calculate the molar mass for all of those, you're going to come up with 310.18 as the total. Okay? Now, since that's the total, that's going to go on the bottom. Calcium, I have 3 of them, and each calcium is 40.08. So if I take 3 times 40.08 and I divide by the 310 and I multiply by 100, that will give me the percentage of calcium in the compound, and I will need 4 significant figures, so that's going to be 38.76%. Okay, same thing for the phosphorus. I have 2 phosphorus atoms at 30.97 each, divided by 310.18, multiply it by 100, again, part over the whole, times 100, and that will give you 19.97%. And then finally, the same thing for the oxygen. 2 times 4 is 8, so I have 8 oxygens at 16 apiece. Divide that by 310.18, multiply by 100, and that's going to give me 41.27% oxygen. Now, a really good way to check yourself is just to go ahead and add up all of those numbers and make sure they add up to 100%. These do. Don't be overly alarmed if it comes up to 100.01 or 99.99. That's going to happen on occasion because of some rounding, so don't let that worry you. If you come up with 78, you obviously are going to have a problem. Just drop my marker cap. Okay, now we can also take this and go the other way with it, and that's if I have percent composition, can I calculate the empirical formula for the compound? So now we're going to work a problem like that. And it says that I've got barium metal that's heated in chlorine gas. And so I find out that the compound that forms is 65.95% barium and 34.05% chlorine. Now, if I have percents, the easiest way to work this problem is just to assume that I had 100 grams to start with. Now, I could assume that I had anything, but the math gets a lot easier if I assume that I had 100 grams. Because then I can just take the percentages. Again, I could assume that I had any starting amount, but a percentage is going to be, it's a ratio, so it's going to be the same ratio no matter what starting compound I end up with. So the simplest way to do it is to assume that you had 100 grams of compound. So with that, the 65.95 percent barium, I'm going to take that and I'm going to make that grams of barium, assuming that I had 100 grams of sample. And just like we've done in almost all empirical formula problems that we've already done, I've got to take grams and I've got to convert it to moles. And from the periodic table, you will see that 1 mole of barium is 137.33 grams of barium. Okay, so grams cancels out, and I end up with 0.4802 moles of barium. Okay, I'm going to do exactly the same thing with the chlorine. They told me it was 34.05% chlorine, so I'm going to assume I had a 100 gram sample, which means I'll have 34.05 grams of chlorine. Put that over 1, change it to moles. From the periodic table, 1 mole of chlorine is 35.45 grams of chlorine. Grams of chlorine cancels out, and when you crunch those numbers, you end up with 0.9605 moles of chlorine. So once again, this should look really familiar. I have moles of chlorine, I have moles of barium. I need to take the smaller of the two numbers and divide everything through by the smaller of those numbers. Well, the smaller one is obviously this one, so I'll divide this by 0.4802, divide this one by 0.4802. So this gives me 1, and this gives me 2 when I divide that out. So I'm going to end up with BaCl2. And thankfully, that also makes sense. It is an ionic compound. Periodic table tells us that barium has a charge of +2, chlorine has a charge of -1, and so that should be the formula that I come up with. Now, you may do that kind of analysis for some other compounds where maybe you're using a transition metal where the numbers change all the time, and you may not necessarily be able to tell strictly from looking at it, oh, this is what the formula should be. But the analysis that you use with those numbers is going to be the same regardless.